Welcome to the class again. We will continue our discussion on organolithium reagents. I will give you some more practice problems. What is the product here? This can be hydrolyzed. So hydrolysis process takes place here. It generates this enol and this enol. Both can be tautomerized to give the corresponding carbonyl molecules. When we have a mixture of furan and thiophene, which can be adolithiated preferentially. Which can be adolithiated preferentially. When this amide is treated with LDA, THF, then benzophenone, and finally hydrolysis, it generates ardolithiation followed by addition to this electrophile, and that will undergo intramolecular esterification as discussed in the previous example. Here, furan will not be lithiated because it is more sulfur. Sulfur can stabilize this anion more compared to oxygen. So thiophene will be ardolithiated compared to furan. LDA is a strong base. It cannot undergo halogen lithium exchange reactions. Only alkyl lithiums will do that. So here it acts as only a base. So it generates an anion here that will undergo nucleophilic substitution on this. One of the SMU will be leaving. So you write the product. In this case also, LDA acts only as a base. It generates an anion here CN is a good leaving group. Again, it will undergo sulfur. It forms a bond with sulfur here. So you write the product. In this case, anion will be generated here. Chlorine is a good leaving group. So silane, trimethylsilane group will be added here. So you write the product. For this example, I'll give the product. You practice how it is coming. Obviously, it will undergo ortholithiation here. So anion generated here will react with one of the phenyl this nitrile group. So nitrile carbon is electropositive. This anion will attack a nitrile carbon. Then C triple bond will, one of the pi bond will be polarized towards nitrogen. So it becomes C double bond N. Then this anion will again attack another phenyl cyanide. So again it becomes N minus. Of course, we know this OET, OR or NR2 groups are good leaving groups. So this nucleophile will attack on this ring. So after losing OET, we will generate this cyclic system. We have just seen ortholithiation reactions. Ortholithiation is also possible not only at the aromatic carbon but at the benzylic position also. For example, look at this molecule, orthotolic acid. When it is treated with two equivalents of LDA in THF, then it is possible to pick up benzylic proton also. Benzylic proton is also acidic. So one equivalent will be used for acidic proton abstraction. Second equivalent will be used for benzylic proton abstraction. So when we use LDA, we can lithiate. So that means it is abstraction of acidic protons. Nothing but abstraction of acidic protons. So this can be further explored. Alkyl halide, it is an electrophile. Here iodine is a good leaving group. So it will undergo alkylation here. Since acidic benzylic position, benzylic protons are acidic in nature, so they can be easily abstracted with a strong base. Here it is LDA. In this case also, we have benzylic carbon, and at the same time we have coordinating group. So when we treat it with LDA, LDA easily picks up this benzylic proton, it generates an anion, and it adds to electrophilic carbonyl carbon that generates alcohol. Of course, we have a amide group that will undergo intramolecular esterification reaction to give this product. So this reactivity, it is simple abstraction of acidic protons. LDA is a strong base. Benzylic position is acidic in nature. So these protons, benzylic protons, are acidic in nature. At the same time, we also have a coordinating group which can stabilize, which can coordinate with lithium. So these oxygens will coordinate with lithium, so they can stabilize this anion here. So that is why lithiation at benzylic position is very easy in these cases. Here also it will undergo lithiation here. Then when it is treated with acetaldehyde, this nucleophile will react with carbonyl carbon. So the product is this. But when it is treated with benzaldehyde, it is undergoing dehydration to generate this product. It is undergoing dehydration also. Acetaldehyde, it is giving alcohol. When we use benzaldehyde, it is undergoing dehydration also, probably due to the extended conjugation offered by phenyl group. Another important reactivity of organolithium reagents is conversion of this acyl anion equivalent. Of course, this can be easily obtained when we have acetaldehyde. Acetaldehyde can be converted to this. Just treat with a base, generally like LDA, that generates enolate ion. Enolate ion can be trapped with methyl iodide. So we will generate this alkyl vinyl ether. Alkyl vinyl ethers, they are called acyl ion equivalents. I'll tell you how. When we treat it with a base, what will happen? It generates lithiation at this place. This molecule, it is equivalent to this one, acyl ion equivalent, acylium ion. When we treat this molecule with alkyl lithium, it generates lithiation at this place. This anion or this nucleophile can be trapped with an electrophile. For example, we are using benzyl bromide, so that will undergo benzylation at this place. And finally, we can hydrolyze this enol ether. So when we hydrolyze it, it becomes enol. Enol will be tautomerized to carbonyl. So in the overall reaction, this methyl vinyl ether is used as a SiO ion equivalent. So this is another important reaction for organolithium reagents. I'll give you one more practice example. You just write the products here. You write the products here. Nitroethane or a carbonyl acetaldehyde protected as dithiene. These are generally called as SL ion equivalents. Why? Here we can generate negative charge here. Similarly, here also we can generate negative charge here. So that can be, that means like this. It can be treated with another electrophiles, and after that, when we do NEF reaction, nitro group will be converted to carbonyl. And similarly, when we deprotect it, it becomes again carbonyl. Okay. So that is why these are called as SiO ion equivalents. Generally, it is not possible to generate an anion here, right? We need to use Umpolang reactivity. Then only we can generate anion here. So how do we generate anion here? We can generate this. We cannot generate this directly, but indirectly when we use this alkyl vinyl ether with alkyl lithium, we can generate this anion, or alternatively we can use nitroalkanes or carbonyls which are protected as dithiones. So these are used as SiO ion equivalents. There is a correction. This is not OMB, this is just methyl group. It is just methyl group. Not only vinyl alkyl ethers, we can also use sulfur compounds. We can also use these sulfur compounds when it is treated with alkyl lithium reagents. Again, it generates an lithiation here. And when we have both these functional groups, thioethers and ethers, now where we will generate this lithiation, alpha to sulfur or alpha to oxygen. The generated we can generate sulfur group can stabilize anion more compared to oxygen. So this position can be alpha to sulfur can be lithiated preferentially compared to alpha to oxygen. So here this proton can be lithiated. So that is why we are getting this product. In this example, we have three potential hydrogens which can be abstracted and lithiated. But when we use but only alpha hydrogen will undergo lithiation. Only it is undergoing lithiation, probably the stabilizing effect of oxygen. Oxygen can coordinate to the lithium. So N-butyl anion can pick up this proton. So probably alpha position to oxygen is undergoing lithiation preferentially. Last two examples. Not only that, benzylic or allylic protons, they are also acidic. So we can easily remove these allylic or benzylic protons. So we can generate allylic anion. This allylic anion, of course, it undergoes resonance. That means either this carbon may react when we use an electrophile or this carbon may react. It depends. Okay. So I'll give you just one example. When it is treated with the same reagents, it is generating this anion. This allylic position, allyl proton can be abstracted, so we can generate this anion. And when we use carbon dioxide, it is the end carbon which is undergoing reaction. So this carbon is undergoing reaction with the carbon dioxide. I'll give the product. I'll write the product here. So it depends which carbon in this allyl system, which carbon will undergo reaction. Okay, these two carbons, either this carbon or this carbon, both are potentially potential anions which will undergo reaction with electrophile. Here it probably the primary carbanion which is less sterically crowded, so that is undergoing reaction with electrophile.